This spacecraft traveled nearly 500 million kilometers. It failed because someone used the wrong units. Guys. On December 11, 1998, a Delta II rocket thundered into the Florida sky. It carried a machine of great hope and scientific promise. This machine was the Mars Climate Orbiter. Its destination was the Red Planet, a world of rusty dust and thin air millions of miles away. The spacecraft represented years of work, a significant investment of public trust resources. Its mission was ambitious. It sought to unlock the secrets of Mars's past, to understand how it transformed from a potentially warm, wet world into the cold, barren desert we see today. The journey it began was a testament to human curiosity, a bold step to send our senses to another world. The total cost of this ambitious endeavor was $327 million. Yet this entire enterprise, this vessel of human ingenuity and scientific aspiration, was doomed from the start. The primary goal of the Mars Climate Orbiter was to serve as a dedicated weather satellite for Mars. Scientists have long been fascinated by the Martian climate. Evidence appears as ancient riverbeds, shorelines carved into the landscape, suggesting liquid water once flowed freely. What happened to that water? What happened to the thick atmosphere that must have supported it? The orbiter was designed to find answers. It was equipped with two main instruments, PMIR, the pressure modulator infrared radiometer, MARSI, the Mars Color Imager. Together they would create a daily global map of the planet's weather and of atmospheric conditions. The mission was part of NASA's Mars Surveyor 1998 program, which also included the Mars Polar Lander. The orbiter was not just a science platform, it was also a critical communications relay. Once in its final mapping orbit, about 421 kilometers up, 262 miles above the surface, the orbiter would begin systematic study of the Martian atmosphere, observing temperature, water vapor content, and dust storms for one full Martian year. About 687 Earth days. The spacecraft was a compact box-shaped craft built by Lockheed Martin Astronautics in Denver, Colorado. NASA's Jet Propulsion Laboratory in Pasadena managed the mission, overseeing navigation and scientific operations. This government contractor partnership is common in space exploration. The plan? Enter a highly elliptical orbit around Mars first, then aerobrake to a stable science orbit, a fuel-efficient approach. Following its successful launch on December 11, 1998, the Mars Climate Orbiter began its long and quiet journey. For the next 286 days, the spacecraft traveled through the vast, empty expanse of interplanetary space. Its path was not a straight line, but a long, curving arc, carefully calculated to intercept Mars at just the right time and place. During this cruise phase, the spacecraft was mostly dormant, with its systems periodically checked by flight controllers back on Earth. The journey was uneventful, a silent testament to the precision of modern celestial navigation. To keep the spacecraft on its intended path, mission controllers at the Jet Propulsion Laboratory had to make small adjustments along the way. These adjustments are known as trajectory correction maneuvers, TCMs. They are necessary because a spacecraft's path can be slightly altered by forces like the gravitational pull of the Sun, other planets, or even the gentle pressure of sunlight pushing on its solar panels. These maneuvers involve firing the spacecraft's small thrusters for a specific duration to nudge it back onto the perfect course. Over the 9-month journey, several TCMs were planned and executed. The spacecraft communicated with Earth through NASA's Deep Space Network, a global system of large radio antennas, sending commands and receiving telemetry about health, position, and velocity. After each TCM, navigators compared expected results with reality. Everything seemed normal, but a hidden discrepancy was present from the very beginning. Each thruster firing introduced a small, persistent error into the flight path. The orbiter was slowly drifting off course, and no one knew the real reason why. Navigating a spacecraft to Mars is an incredibly complex task. It requires a team of highly skilled engineers, known as the navigation team, at the Jet Propulsion Laboratory. They use the data sent back from the orbiter combined with powerful computer models of the solar system to determine its exact position and velocity. This process is like trying to track a pebble thrown across a continent, knowing exactly where it is and predicting precisely where it will land. To make course corrections, the navigation team relies on small thrusters. When they fire, hot gas creates a force in the opposite direction. The push delivered is called an impulse. The team calculates the exact impulse needed, then commands a specific thruster to fire for a specific amount of time to achieve that impulse. It is a delicate process of nudging the spacecraft back onto its invisible highway in the sky. Because thrusters are not perfectly consistent, engineers use a small forces file. Ground software from Lockheed Martin compiled tiny impulses for JPL to ingest into trajectory models. The system was designed for accuracy, but the chain of communication and verification began to break down. Lockheed Martin generated the data one way, JPL software interpreted it another. Critically, no automated check confirmed the format. The two teams were, in effect, speaking different mathematical languages, and neither was aware. To understand the failure of the Mars Climate Orbiter, we must first understand the two systems of measurement at the heart of the mix-up. In science and engineering, force is measured in specific units. The international standard, the metric system, used by NASA and scientists globally, measures force in newtons. 1 newton is the force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. For thrusters, the total impulse, change in momentum, is measured in newton seconds. In the United States, the English or imperial system is still used in some engineering, particularly aerospace. There, force is pounds force, and impulse is pounds seconds. Both units measure force, but on different scales, not interchangeable. 1 pound force is significantly larger than 1 newton. The conversion is straightforward but critical. 1 pound force is approximately 4.45 newtons. Therefore, 1 pound second equals about 4.45 newton seconds. If you expect newton seconds but are given pound seconds, the value appears 4.45 times larger if read as newtons. Conversely, if you expect pounds but are given newtons, it appears 4.45 times smaller. In the Mars Climate Orbiter case, Lockheed Martin software produced thruster impulse data in pound seconds. That was in the software requirements. But the JPL navigation software used those numbers as if they were in newton seconds. So when Lockheed reported, for example, 1.0 pound second, JPL read it as 1.0 newton second. Because a pound second is 4.45 times stronger, the navigation software underestimated the effect of every thruster firing by that factor. The unit mismatch created a slow, creeping error that built up over the entire 9-month journey to Mars. Every time the spacecraft fired its thrusters for a trajectory correction maneuver, the navigation software at JPL underestimated the resulting change in velocity. The spacecraft was being pushed slightly harder than the navigators believed. Consequently, with each maneuver, the orbiter strayed a little farther from its intended flight path. Small daily errors became significant over 286 days and millions of miles. One might wonder why such a persistent error was not caught sooner. The investigation that followed the loss revealed several reasons. The navigation team did observe discrepancies after maneuvers, but attributed them to normal variations and adjusted models without identifying the root cause. The team was overworked, and the mission was part of NASA's Faster, Better, Cheaper initiative. This environment may have led to less rigorous oversight and fewer cross-checks than on previous, more expensive missions. There was no dedicated independent team tasked with verifying trajectory calculations end-to-end. The small forces data was accepted without a simple unit check. It was a classic case of assumption. The final trajectory correction maneuver, TCM-4, on September 15, 1999, 8 days before arrival, was the last chance to fine-tune the approach. By then, the cumulative error was substantial, but models still indicated a safe path. They believed the spacecraft would pass about 226 kilometers, 140 miles above the surface, a safe altitude for orbit insertion. On September 23, 1999, the Mars Climate Orbiter arrived at its destination. The flight control team at JPL was gathered, ready for Mars orbit insertion. The plan was for the spacecraft to fire its main engine for 16 minutes and 23 seconds. This burn would slow the orbiter to be captured by Mars's gravity and enter a long, elliptical orbit. As the spacecraft passed behind Mars, a planned loss of radio signal began. The team expected to re-establish contact shortly after the burn, but the trajectory carried it much lower than planned. Navigation predicted a closest approach of 140 to 150 kilometers, about 87 to 93 miles, above the surface. However, because of the accumulated error from the unit conversion mix-up, the spacecraft was actually headed to only 57 kilometers, about 35 miles. This was deep within the upper layers of the Martian atmosphere. Traveling at about 5.5 kilometers per second, over 12,000 miles per hour, aerodynamic forces and heating spiked. The delicate spacecraft, with its large solar panel and fragile instruments, lacked a heat shield and the structural integrity for such stresses. Atmospheric forces tore it apart. Intense heat incinerated the fragments. Back on Earth, the minutes ticked by. Expected emergence and radio contact came and went. Deep Space Network antennas listened for a signal that never arrived. At first, there was hope, perhaps antenna orientation. But hours passed with no signal, and a grim realization settled. The Mars Climate Orbiter was gone. It had not entered orbit. Instead, it met a fiery end in the very atmosphere it was sent to study. The loss of the Mars Climate Orbiter was a stunning and deeply embarrassing failure for NASA. The total cost, $327 million in 1999, was a complete loss, equivalent to over $600 million today. It represented not just hardware, but years of dedicated work by hundreds of scientists and engineers. Beyond finances, it was a blow to agency prestige and Mars exploration momentum. Its relay role for Mars Polar Lander was lost. The lander itself would fail later for unrelated reasons. NASA convened an independent investigation board led by Arthur Stevenson, reviewing specifications, data exchanges, and communications. They uncovered the fatal unit mismatch. The final report in November 1999 stated plainly, the root cause was failure to use metric units in coding a ground software file. The data required Newton seconds, but was provided in pound seconds. The board cited deeper issues: inadequate training, poor communication between JPL and Lockheed Martin, insufficient oversight. NASA implemented sweeping changes, emphasizing risk management, independent verification, and clear communication protocols. Software and data interfaces would receive rigorous testing. The faster, better, cheaper philosophy was re-evaluated with a new understanding. Cutting corners on verification and testing is a false economy. The loss became a powerful, costly lesson in attention to detail. The Mars Climate Orbiter is permanently lost. It either burned up in the Martian atmosphere or was torn apart by aerodynamic forces on September 23, 1999. Its fragments likely scattered across the northern plains of Mars, silent relics of a mission that never began its scientific work. The mission was a total failure. It achieved none of its scientific objectives, and its relay role could not be fulfilled. The ultimate lesson is simple but profound. Assumptions are dangerous in engineering and science. The JPL team assumed the data from Lockheed Martin was in metric units. Lockheed Martin assumed their data would be used correctly. Neither team verified this fundamental assumption. In complex systems with many groups, clear communication and rigorous verification are not optional. They are the bedrock of success. The smallest detail, like a unit of measurement, can unravel an entire endeavor. This incident is now a classic case study in engineering and project management courses worldwide. Human error is inevitable. Systems must catch errors with checklists, independent reviews, end-to-end testing, and clear interface agreements, the safety nets that prevent catastrophe. The orbiter was not lost because of a single person's mistake, but because the system of checks and balances was not in place. The story ends not with data from another world, but with a question for all of us who build and create. How many of our own complex systems, in software, in finance, in infrastructure, rely on unstated assumptions? How many unit conversion errors lie dormant, waiting to cause a failure? A simple lesson. Progress doesn't just require innovation, it demands attention to the smallest details that decide success or failure. Thanks for watching. Please subscribe for our next decoding of another wonder and let us know what you think.